wanted to understand, if we just put some data on the input of a neural network, what's going to happen to that data, right? So there are a bunch of numbers. There is only computation going on here, right? So you have your input in the first very beginning, like layer 0, the input layer. And these guys are going through these neurons, right? And then every time they get to a neuron, they're going to get to multiply with a bunch of weights, which are specific for that neuron. And then they add up and then get activated, right? And same thing going to happen in the next layer, and next layer, and next layer. And we talked about it. Each layer is somehow computing a bunch of features about the input, right? So the features that you see at the output of the first layer are supposedly a bit better if you assume that this neural network is working fine, right? So you assume that, for instance, this is doing a pattern recognition or a classification, and then you're going to put your image in the input, and at the output you're going to see what is the pattern, or, for instance, what is the class of that particular image, right? And in the first layer, supposedly it's going to give you better features as compared to image itself. Then in the second layer, it's going to give you much better features as compared to the previous set of features and the input, and so on until you get to the very output, right? So when you arrive at the output, you probably have enough features that you can conclude whether this is image of a cat or dog, right? So that was the idea, and we tried to write down everything, right? So at the end of the day, I mean, we did a bit of like notation and computations, but at the very end of the day, we concluded that the connection between this layer, every variable in one layer, and the variable coming out of the next layer, how we can present it? Do you remember? It was a matrix vector product being activated, right? So I can compactly show it right like this. This is going to help us today when we are doing a computation graph. We want to compute the gradient. So the idea is that here you have your input, right? This is going to get multiplied with a matrix. And this matrix is eventually computing those z values, right? The values which are at the input of the activation, and then it gets activated, right? And so on. Every layer has its own weight matrix. And this weight matrix is the one which we are going to design, right? The weights inside this weight matrix is the ones which we can play with and just tune to get the right model, right? So this is a kind of compact model that we are going to use today quite a lot, because this is going to make life much easier when we want to just do the gradient computation. So the idea here is, as I told you, whatever goes inside. So if you're thinking about one particular layer L, so whatever you have from previous layer, this is YL minus 1. You remember that we used to add this dummy 1 to just take care of the bias, right? And this whole thing here is what is coming at the in the layer L, right? So if you think of layer L, this is what you're going to see at the output of these nodes, right? And these outputs are going to get multiplied with a matrix. So the dimension of that matrix is set in a way that it's going to match the dimension of the next layer, right? And then you're going to have the z value. So z was the one which was computed before activation. So it's a fine transform, the linear transformation of the layer output, right? And then you're going to do the activations. So this FL is, for instance, ReLU or sigmoid function. It's going to look at every single entry and simply activate them, right? Pass them through that operation. And you're going to have your next output YL, right? And as I said, this one, this particular value 1, is the one which is taking care of the bias. We're going to mention it less and less as we go through the course. Okay? So everybody recaps, right? Everybody remembers what we did last time, right? Okay, cool. So if you can remember that, now the next thing that we need to do, we need to train this neural network, right? Meaning that we are going to look into a bunch of images that we have, into the data set that we have and their label, and we try to make this model to somehow give us the right output for those data samples that we have inside our data set, right? And if we want to do it, what should we do? What was the idea? Like the general idea in machine learning. So we have the model. The model is the neural network. We have the data. We compute the loss, right? We just average it over all the samples that we have. We called it empirical risk. And we try to minimize the empirical risk, right? And if we want to do this minimization in an algorithmic way, what is the right algorithm to use? This is the gradient descent. So we need to compute the gradient in each step, and then we move in the opposite direction of the gradient. This is supposedly taking us towards the lower value of the loss, right? So that's going to be the idea, but you might guess that, or you might see it right now, that this gradient that you want to compute looks quite complicated, right? Because of the forward pass that we have, right? So a bunch of weights in the first layer are going to impact the input, right? So these are a bunch of parameters we want to compute the gradient with, but then these outputs are going to pass through the next layer, right? The weights of the next layer are again involved, right? And so on towards very end, right? So this is a kind of complicated set of functions in terms of those weights, and this is going to be a hard thing to compute the gradient. This is why we developed the algorithm called backpropagation, which is nothing but the chain rule that many of you know from high school. So that is basically that one, but we try to just write it down in a systematic way that's going to help us efficiently compute the gradient, okay? Everybody's clear? So one thing from this very beginning, backpropagation, even though many people say this, backpropagation technically is not training your neural network. Backpropagation only computes gradient. Those gradients are given to gradient descent to train your neural network, right? But many people shortly say that backpropagation is used to train this model. It means that backpropagation was used to just compute the gradients, okay? At the end of the day, you are using one gradient-based optimizer. So now, let's write down the training problem. So this is the classic training problem that we have. We have x's. These are the data samples. We have v here, which is the true label. So when we started, we used to show it by y, right? The true label. I'm going to use it from now on by v because I want to show the output of the neural network by y, and I want to have enough distinction that you don't get confused. So when you see v, this is the true label that you have inside your data set. For instance, you have the image of a cat, and then v is simply the class of cat, right? Now, this v in general, you can think of it to be a vector, right? There is no problem with that, for instance, if you think of the regression problem, right? So this is why I keep it as a vector, but we're going to see that like when we deal with the classification problem, most of the time this is just an integer, right? But that is not a big deal right now, okay? So v right now could be a vector, and yeah, that's it. So what we want to do, we want to just train the neural network. So what we're going to do, we're going to get every single sample that we have, every single x. We're going to pass it through the neural network. So the forward propagation is going to happen, right? So you have a bunch of weights fixed on your neural network. Data goes in, the pixels of your image go in, and then they are going to propagate over this neural network by those computations, and you're going to see one output. This is what I'm going to call it YB. This is the output of the forward pass when you pass XB through the neural network. And this neural network has a bunch of weights, right? Those weights are basically the parameters you have in all of those matrices in between, right? And I can just sort them out in one vector W, right? This vector now is a giant vector, right? Because it's going to include all the weights inside the neural network, right? So we have this one. This is Y, the output of the neural network. And the thing that we want to do, we want to make this Y to look like V as close as possible, right? And we do it by simply computing the loss, right? So that was the idea of training. So at the end of the day, we're going to get this y and compare it with v, the original label, using the loss function that we have. So we compute the difference between them. And then we have capital B different samples. So we're going to average over all those samples. This is supposedly the good estimator of the risk that we want to minimize, right? This is what we called it, the empirical risk, right? So we want to minimize this guy. One point here. What is the variable of this minimization here? W, right? The weights. So x's and v's are fixed. They are given by the data set, right? You're not computing any gradient with respect to them, right? They are given numbers to you, right? You have your image and it's labeled. The thing that you want to change are weights, right? So the variable of your optimization is W. You should pay attention to that, right? Everybody's cool? Okay. So we want to do that. So basically, we want to just minimize this guy. And if I want to think about this, where does, I mean, this term that you see here, we're going to use this notation quite a lot in the rest of the course. But one thing that you should always pay attention to is that where this W is actually involved. Where is W in this expression, in the expression that you have in the right-hand side, in this average? It's within Y, right? So Y is including that W, right? So this is there, but if I want to just show the relation very explicitly all the time, it's going to get a messy notation, right? Yes?
Do we just assume the bias is
within the weights, right? You don't need to worry about that anymore. I mean, you're going to see gradually that you can simply forget about this. But yes, biases are there. I'm going to show you for this particular fully connected network, how does that W look like? Just, yeah.
How wide do we divide by B if it doesn't affect the optimization?
Sorry?
How wide B, like, why we divide by B if it doesn't affect the optimization?
B?
Yeah.
It does not depend your optimization algorithm. I'm going to show it quickly. So you actually...
why we need to do that?
Why we need to consider B?
Yeah, like...
We're going to drop it. I mean, originally when we defined the training, we said that we want to minimize the average, right? Correct? So, I mean, this 1 over B, you can simply drop it, but right now I haven't told you what you can do with the summation, right? So this is just for sake of complete length, right? But we're going to get rid of that soon. Questions? Okay, cool. So if I want to do this minimization, what should I do? We said we want to do gradient descent. What does that mean? That means that this empirical risk that we have, this average term that we have, this is a function of weights. And it's good to first think, how does this algorithm look like? So you're going to start with some weights, right? So you are going to initiate your neural network with a bunch of weights, right? And then once you started that, then you're going to get into the loop, right? So you would say, okay, a bunch of new weights are going to be the one I started with minus learning rate, the gradient of this term with respect to the weights, right? So the gradient of this term with respect to the weights is exactly the same dimension as the weight vector W, right? And then you're going to have one gradient vector, which is giving you the right direction to move. And then you just subtract it, right? Now you compute the new bunch of weights. It's like you get your neural network, you change the weights inside your neural network, right? Again, you are going to look at the risk function. So you're saying that this new risk, the average loss that I'm getting, how does it look like as compared to what I had before, right? If it's changing, then you would say, okay, this says that I could potentially get better, right? So you keep on training. So you go next, you get the new weight. Again, you compute the gradient, right? And then you update your weights. Again, you take a look at your risk. If your risk is dropping yet, you keep going, right? At some point, you see that your risk is not changing. This is the point where you get close to the minimum, right? And then you would say, okay, I am right now in the minimum. My gradient descent algorithm is not taking me anywhere anymore. So I'm going to stop, right? This is when you see this delta is small and you're going to stop, right? So the whole idea is that every iteration of the gradient descent that you do, you need to know the gradient exactly at that point, right? This means that when you updated your weights, you need to compute the gradient from scratch, right? New gradient. It's not the previous gradient anymore, right? You cannot use that anymore. So in every iteration of your gradient descent algorithm, you need new gradient, right? Everybody's cool? Okay, so this is the kind of algorithm that we need, and obviously the guy who is challenging is this blue guy, right? The gradient term. If we come up with an algorithm which can compute that gradient for us, then that's over, right? We can just use this algorithm efficiently. Yes?
Just wondering, in the while loop,
Okay.
in the while loop, when you update the weights, it's based on the batch, right? Instead of, I don't know, because
We haven't talked about that now. I do know what you want to say, but we haven't talked about the mini batch and stuff like that. We're going to talk about that later. You think about the full batch training right now. Full batch.
like in the formula, like the whole data set.
Yeah, the whole data set. You think like that right now. We're going to make the mini batch later, right? So right now we assume we can do it, right? Okay. Questions? No question? Okay, cool. So if you got no question, then first of all, let's look at this vector of the weights, W, right? So this guy, as I told you, this is a quite giant vector, right? So it's going to look like this. So I'm going to go for the first layer. I would say in the first layer, first hidden layer, I have W1 different neurons, right? Every neuron has a bunch of weights coming from the previous layer to it, right? So lots of inputs are getting connected to the first neuron, for example. This is going to have its own vector of weights, right? This is for the first neuron in the first layer, right? Second neuron in the second layer. Third neuron in the, second neuron in the first layer. Third neuron in the first layer, and so on, till last neuron in the first layer. I am finished with the first layer, I go for the second layer, right? First neuron in the second layer, second one in the second layer, and so on, till it's finished, and so on, till I'm finished with all the neurons, every single neuron I have in my neural network, right? So I'm going to put all the weights next to each other, and of course you see that every single of them is again a vector, right? So if I'm thinking about the particular layer L and neuron J in it, it's going to be connected to every single other guy in the previous layer, right? Clear? And every single of them has its own weights, right? Correct? And they have biases. The biases we said we're going to show it with this index 0, right? So this is the bias guy. These are the weights, right? So what you can think of this guy, it's a giant vector including every single weight and bias you have in this neural network, right? And you can choose your own order, right? I put it this way. Maybe you start with the first neuron, and then you go for the last neuron, and then you can put it in the order that you want. It's not going to harm anything, right? But at the end of the day, everybody here is a weight, right? So it's safe that I would say that if I think of one entry here, one single entry here, this is weight of one layer connecting one neuron in that layer to one previous neuron, right? That's safe, right? It's the weight on one of the edges that you have, right? One of them, right? And how many edges you have, this is exactly the number of weights you see here, right? Everybody's cool? Okay, now, the thing that I want to do, I want to compute the gradient. If I want to compute gradient, what should I do? I should compute the partial derivative with respect to every single of these weights, right? So I should see how does this particular risk function r hat is changing as compared to every single weight. If I change tiny bit in that weight, what can happen to that risk, right? Everybody's cool? You see it? Okay. So basically every single entry that I have is going to look like this, right? This is one partial derivative with respect to one of the weights, right? And now if I want to compute that, what should I do? I should say that, okay, first of all, I'm going to write down this r hat expression. This is 1 over b, the average, sum of all of those losses, right? Now, can I take the derivative into the summation? Does it harm? Is it any problem that I first take the derivative and then average? No, right? Derivative of f plus g is derivative of f plus derivative of g, right? So I can do this, right? I can do like this, right? Now, if I know how I can compute the gradient or the partial derivatives, of loss at one single point, that's enough, right? Because I just need to compute that particular gradient for that single sample. And if I have all of the sample gradients, then I'm going to average it, right? Everybody's cool? So that's the point. You don't really need to think about all the samples inside the data set. It's enough that you think about one single data point, right? If you can come up with a solution that computes the gradient of the loss at that single data point, then the only thing that you need to do in order to compute the gradient of the risk function is to just average those sample gradients, right? Everybody's cool? Yeah. Yes. Oh, yeah, this is wrong. This is a typo. Yeah, this is typo, sorry. So it should be W-L-I-N-J. This is a typo, just, sorry. Thanks. Yeah. Yes? Yes, definitely.
They won't be the, so if you do it at only one single point, the other ones could be.
No, by single point I mean single x, single data point, single y, right? One of the samples inside your data set. And of course you need to compute the whole gradient, right? So if you feel more comfortable, you can drop this partial derivative and you can just write it down the gradient, right? So you only need the gradient of one sample point, right? Questions? Sorry? Previous slide, what is there? Yeah. Sorry?
Can you please explain this a little bit extra because I didn't get it?
Yeah, I was just trying to explain what is this vector weight. This vector is including all the weights that you have, right? For all the neurons inside your neural network. So you would consider the first layer, then the second layer, and so on, right? And then every single entry inside these tiny vectors here, or it might be not even tiny, right? But it's smaller as compared to W itself. Every single of them are the weights of the neurons, right? So when you think about this vector, it's like you randomly choose one of the neurons inside your neural network, and then you just choose another neuron, and you look at the connection between them, and this is the weight that is showing, right? And how many of them you have, this is going to exactly be the size of your W, right? Okay. Okay. Yes? Yes? Sure, sure. No, weights are different. This is this guy. The one that you said is this part. Yes. I would change. This is why we have a vector for that, right? So it's going to get, this neuron is going to get connected to the bias and also all previous outputs with different weights, right? Yeah. Everybody's clear? Questions? Yes. Yes.
So on the right-hand side, you have the W on the second index, where it indicates how many weights you have for the previous layer, right? But why on the left you have W1 in the first index as well?
W1 here? This W1, I mean the weight in the first layer, first neuron. Weight in the first layer, last neuron. So it's like this. So maybe I just show the diagram. So say, for instance, you have three neurons here, right? And then you have, say, three inputs. So here is X1, X2, X3. And then you have the first set of neurons. And then here you have two neurons. And then you have your final one neuron. OK? Then this guy, I mean, supposedly all of them are connected to this one, right? So this is layer 1. Layer 1. So I'm going to put 1 here. And then to show the weights of this guy, I'm going to just call all these weights, including the bias. So if you have a bias, there's going to be also a bias here, right? So I'm going to show them using this notation. W1, 1 is this index, right? And then I'm going to look at these guys, right? So this is j equal by 1, j equal by 2, j equal by 3, right? So I'm going to say W1, this is weight of the first layer. The first neuron, this is the first neuron, right? And then everything coming from previous layer, right? And now, how many of them I have? 1, 2, 3, 4, right? So supposedly, again, this guy is going to look like this, right? W1 of 1 coming from 0, right? And 0 is this index, right? Here I equals by 0, I equal by 1, I equal by 2, I equal by 3, right? Okay? So this is going to be the weight, this one. This is exactly this weight. Weight coming to the first neuron in the first layer from I equal by 0, right? And then W1, 1 coming from 1, and so on. W1, 1 coming from 2, W1, 1 coming from 3, right? So this is the weights coming into this neuron, right? What about this neuron? Again, going to have its own weights, right? So there are, again, going to be a bunch of new weights. So you're going to have this one connected to this one connected to this one connected to this, and so on, right? Yeah, this one is now, if I want to show these guys, this is going to be W, still layer 1. The index here is now being j equal by 2, right? 2, and everything coming from the previous layer, right? Yeah? Okay. So now if you want to think about the giant vector W, what you're going to say, okay, I have this vector W. I'm going to first put the weights of this guy, right? So it's going to be a vector of size 4, right? I'm going to have another vector of size 4. I'm going to have another vector of size 4, right? So it's going to be this W1, 1, everybody. So this guy is of size 4, right? And then you have your next W, W1, 2. This is again of size 4. And same thing, W1, 3. This is again of size 4, right? Then you go for your next layer. This is your next layer. You're going to say, now I am in the second layer. This is now the first guy in the second layer. And then everybody's connected. Now again, if you want to think about this, so you're going to have one bias here and 3 different outputs. So you're going to be 4. Again, you're going to be a vector of size 4, right? So you're going to have here W2, 1, everybody. This is of size 4, right? And same thing going to be for the next one. So it's going to be W2, second neuron, everybody. This is of size 4, right? Now the last guy here is going to be connected to these two, right? And this is going to be another one here, bias. So this one is going to have only W3, the last layer, first guy, everybody, right? And this is going to be of size 3, of course, because you have one bias, two outputs, right? So you're going to have W3, 1, and everybody, which is of size 3. Now you can think of this whole vector to be like 8, 12, 16, 20, 23, right? So it's going to be of size 23. And now if you want to compute your gradient, the gradient of your r hat with respect to W, this is going to be again a vector of size 23, right? And every single entry that you have there is going to be the partial derivative of r hat with respect to one of these weights, right? So it's going to be one of the weights in one of the layer, j and I, right? Everybody's cool now? Yes?
Slight precision, the gradient, wouldn't it be
23 dimensional. It's a 23 dimensional.
right, but it would be it's a row vector.
It's a, we always consider column vector. If I want to just make it row vector, I'm going to put a transpose here. When I write transpose, then I'm going to get a row vector. Yeah? Okay. Everybody's cool? Questions? So now it's clear, right? Yeah. Yes. Yeah, sure. This is just for this example, right? It depends on your architecture. Yeah. Which one is a square? Sorry. Oh, the matrix, you mean. That big W matrix. That is not necessarily a square. Definitely it's not a square. It depends on your input-output size. Definitely, right? Yeah. Everybody's cool? Okay. Great. So now, then let's just go ahead with this one. So everybody's happy with this idea that I don't really need to compute the gradient for all the samples, just I need to compute the gradient for one sample point, right? So if I compute the gradient for one sample point, then when I average it over all the samples that I have, it's going to give me the gradient of the risk that I want, right? So at the end of the day, the whole computation task that I have is to come up with an algorithm which can look at one sample point x and v, right? X as the input, v as the label, and be able to compute the gradient of the loss, right, with respect to the weights. Everybody's cool? Okay. Now, this guy, this particular L, right, computed at one point, this is what we typically call it sample loss. Because this is computed for one sample point, right? When you change your sample, this value is going to change, right? So this is what we call it sample loss. And sample loss, if you think of your x randomly generated, this guy is also random, right? This is one point. Now, if I compute the gradient of that loss, many people call it sample gradient, right? So you compute the gradient of the loss at one sample point. This is sample gradient, right? Again, if you just choose your x and v's randomly, that sample gradient is going to be random, right? This is important later when you want to just understand the variance and mini-batch training and other things, okay? Right now, the key thing that we want to do, we want to just come up with one algorithm which is able to compute one sample gradient. It means that I just think about one sample point x and its label v. Then I'm going to pass this sample point through my neural network. I'm going to get y, and I compare only that y with the corresponding label v, right? So I don't think anymore about so many samples that I have inside my data set, just one of them, okay? Everybody's cool, right? Okay, so what we want to just do now, we want to just compute the gradient of this particular sample loss. And you can see that this guy is a nested function of the weights. Now, what is the nested function? We're going to explain it next. But everybody's clear what we are going to do now, right? So you have a clear idea how does your function look like and what you are computing, right? One sample point going through the network, you get the output, you compute the loss. That loss depends on all the weights, right? Weights, not the sample point, weights. And you want to compute the gradient with respect to the weights, right? Okay, cool.